constantly needing to move from one system to the next system that just the company absolutely wants to have for one reason or another, and you have to get the data out of the old system into the new system. It's not ideal, but in the real world, a lot of DBAs have to deal with that constantly. And then the other thing that DBAs need to deal with is trying to communicate to technical business people that might not be part of IT or might not have database-specific knowledge. So I'm going to be talking about how to use logic and relational databases to get some more precision in those processes. So I'm going to first some kind of logic preliminaries. The reason logic is important in a database is because it's certainly been around a lot longer than computer science, for one thing. So there's already a lot of it's built on intuition, how humans think and reason, and it provides the consistency, or at least the ability to determine whether a bunch of facts, which is all a database is, are consistent. It's also very unambiguous, which is perfect for this application. And so all those things make logic important, and it's one of the foundations of the relational model. Predicate logic specifically is what the relational model uses. So here, and by the way, this is a reference to Portland, Oregon. Basically, a predicate is just a truth value function. You have it returns some kind of Boolean result. It's got some number of parameters, and when you evaluate a predicate, for instance, there exists a city name with population pop, then you can get either a true or false answer from that. Portland has about 500,000 people, not 50. So the former is true, the latter is false. A predicate with no parameters is just a proposition, just a fact. You guys may all know some of these things already, or similar exposure to logic. The other element of the relational model sets. So the relational database is just sets applied to sets in logic theory applied to data management. Sets are, of course, how pretty much all data manipulation is done. You can't possibly make a special case out of every fact you know. You need automated processing, and the way we do that is sets. A for loop, even though it's kind of a sequential process, is often just used for essentially operating on a set of data, but usually has a lot more context around it than the sets in a relational database. So every relation has a predicate. The predicate is what's used to kind of determine the meaning of all the tuples inside. It's kind of a form, or the form of all the tuples, or all the propositions in the form of tuples can be applied to the predicates. And so basically that's how you know everything in the relation is true. Everything that would be true is in the relation in the form of a tuple that matches that predicate. And everything that's not in the relation you just assume to be false. So this is a little bit of a digression, but oftentimes when you see a picture of a relation, or if you see an XML document, or if you see a spreadsheet, these are all ways of viewing data sets. And when you see one of these things, you see labels. XML is very label oriented. They're called tags, but it's, I'll kind of use labels as a general term. So similar with a picture of a relation in Postgres, if you use PSQL, you're going to see essentially a table-looking thing, and the attributes kind of act as labels for the meaning of that data. That has some limitations, though. One of the aren't necessarily obvious right away, but if you try and assign meaning to an attribute just in isolation, then it's very hard to capture the meaning accurately, except in the simplest cases of data. And even then, you kind of lose it a little bit. So I've got some examples here. If you have very simple data, company C has budget B at location L. You can remove, you can take those in different combinations and so forth, and still end up with true statements. For instance, if you have, a company C has budget B, well, that's true even, in addition to company C has budget B in location L. You've removed the location L attribute, but it's still true. And so you can kind of remove attributes almost at will if the information that you're representing is simple. When you have things, especially involving multiple keys, multi-column keys. For instance, in this example here, you're talking about a budget of a company in a certain year. You obviously can't remove the year at will and still have a true statement in the general case, because year almost distributes to both the company and the budget part of the statement that you're making. What I'm getting at here is that it's very difficult to represent a more complicated predicate like the lower predicate there with just simply trying to assign meaning to an attribute, trying to describe the meaning of year in isolation from the meaning of budget, like you could do in yearly. So that's what I see. It's kind of a weakness of trying to represent data, not using predicates, which are full complete fact like we have here, but just as an individual label and trying to say that year means this, budget means that. It's very hard to really get an accurate meaning if you're just defining the attributes in isolation. Another thing, this is kind of a digression from this digression, but notice that these predicates, although they're truth value functions, they're actually evaluated by humans, of course. A computer doesn't know when a company had a budget necessarily, so the truth of that is actually evaluated by people, and you just try and make your database able to check the consistency as best you can. So these are functions that would be evaluated by humans, whether they're true or not. So I'm just kind of I'm going to go into some examples here in a minute, but I just wanted to just kind of building up some of the relational operators and what they actually mean. The biggest point of my presentation is that relational operators don't just do something. For instance, a for loop does something, a join does something. But the difference is a join actually means something. So if you have a join, it actually, it's at the logical and of the predicates of the relations that you're joining. So that's important because other data models don't really offer this capability here. For instance, it would be hard to come up with a logical meaning of a for loop without all the context around what you're iterating over, that type of thing. There's a lot of context there. It's something the programmer understands, and it's only the only meaning is in that context, and it's relies heavily on the reasoning of that particular developer in the context he sees in the version of the application that he's developing at that time. So that's more fragile than this context-insensitive relational operators. So here we have, for example, join is and. If you have relation R1 and R2, predicates have the meaning company C makes part P, and the relation R2 has the meaning part P requires material N. If you join those, the resulting predicate, or the resulting relation, is simply the logical AND of those two original predicates. And that's very powerful because just knowing the meaning of the first relation, the meaning of the second relation, and what operation you're performing, you know the meaning of the third relation in a context-insensitive way. You're not bound to specific surroundings of the operation, the data that's in the table specifically. It's completely free of that. You don't need to know what data is in the table to know the meaning of the predicate. Got a few more cases here that I won't go into as much detail on all of these, but just as an example, where has a meaning also. The meaning of where is and as well. It's used in a little bit different sense. You could kind of look at it as a join against a virtual relation, maybe, but it's essentially the same meaning. Union is or. So if you have, a student has a name and address, a teacher has a name and address, the union of those two tables is going to be, either a student or a teacher has this name and this address. The union operator means that directly. Projection is the existential operator. So it just means it's a little bit counterintuitive because you wouldn't necessarily think that it's quite so complicated when you see it at first. Back to the labeling example, you typically think if you project away or remove just one of those attributes from the relation, that the meaning is very straightforward. It's not necessarily, as we saw with the example of, a specific year that a specific fact is true. Although it's actually true in the case of a simple ANDed predicate, as we saw in the slide a few slides back, there are many examples where that's not true, and it actually is subtly more meaning here, because you're saying there exists some location L such the company C is located at L. If you're familiar with logic, you'll recognize that as being L is now a bound variable rather than a free variable, meaning that you have one fewer parameter, which makes sense in conjunction with the narrower table. So I'll just kind of move through these. Not is kind of an interesting one in the sense that you wouldn't use that kind of an operator directly. There are too many things that are not true to list. So it could be used in defining other relational operators. For instance, if you wanted to, you could actually define a complete set of relational operators with just the not operator and the and operator, similar to Boolean functions. So let me jump into an example here. Okay, so I'm using here the example Pagilla database. I guess, is that how it's pronounced, Robert? Pagilla?
I think I pronounced it Pagilla.
Pagilla, okay. The example Pagilla database.
I wrote this schema, I don't know
So this is a kind of a video rental store example schema with example data. And so what we've got here is we can see a lot of these tables here. Rental, we can see rental. Can you read that? Should I make this bigger here?
It's fine from here.
Okay. So you can see all. see here, it's some fairly intuitive meaning to a lot of this. So we can make some assumptions about this. We're pretending now that, let's say we're trying to migrate away from this system to some other system that's been, decided on by the company, and you want to take all the information out of here that you can, extract as much meaning as possible, put it in the new system. And to do that requires, you to make assumptions, test those assumptions. You have to look at the data, unfortunately, many times, just because often it's not going to be so perfect. In this example, the Pagila database that I downloaded was pretty much perfect because it's example data. So I changed it slightly so that that was no longer true. But I won't submit a patch. I would assume that it would be an unwelcome patch to break the data. But
is there a procedure that's called swap? Just tweak. That way someone can have perfect data and something that matches it.
Yeah, it would be useful.
oh, okay. Maybe it would be useful. It might be kind of outside the scope of the sample database, but that would be. I think it's useful for this purpose anyway to change around at least a small amount of the data. So, as always, I'm, going to make some assumptions about the data, and then we'll test those assumptions. So the assumptions are, we saw an inventory ID. Well, intuitively, we're going to assume that the inventory ID identifies a specific item in inventory. And then we're also going to assume that rental date is the date that the item is removed from the inventory, and the return date is the date it goes back into the inventory. Well, the implication of that is that no item is going to have a return date that is between that overlaps, or I should say no item is going to be removed from the inventory when it's not there. So we're going to test that with an example here. We're going to, this is a self-join, but we're going to test our assumptions that to see whether they hold up and what the cases are where they don't. So here's a simple query. This is a join, a self-join on the inventory ID. So if it's got the same inventory ID, it should not be pulled out of the inventory when it's not there. So we can run this. And so, sure enough, that found something. We expected that result to be 0. If we look back at the file, what we're expecting the result of this to be is essentially an empty relation, just false. This should always be false. It should never be true if our assumptions hold up. So we see that there's an exception, and sure enough, you can see, let's find the other examples we can see. So we'll look at the other items with the same inventory ID. And so if we kind of browse through this, we can see the source of the problem. If you see the rental date, there's one record. So here's the record that we found that was an exception. And the one with which it conflicts will be another record with an overlapping interval, which is yes, correct, thank you. Okay, so it conflicts with the one below it because it's pulled out of inventory before it's put back in. I think that this is it's a fairly simple but an interesting example. I think I'm trying to show the process that I would go through when migrating one system to another. And this right here, from a logical perspective, it's pretty easy to break down. Logic helps most when it's complicated, and there's a lot of things involved, and it's hard to differentiate, or it's hard to reason when things get so complicated that you can't hold it all in your brain at once, and you'd like to be able to convince somebody else that these things cannot all be true at the same time, and therefore one of the assumptions is wrong. So here, like I said, is a join on inventory ID. So that's basically saying that the two relations, the common attribute inventory ID is a common attribute. The others are distinct attributes. And additionally, this I look at as an overlaps operator. In SQL, that's not necessarily easy to express. This is a fairly naive way of showing overlaps. It's just a simple, straightforward way to say, okay, there's no possible way that it was back in the inventory if this is true. So back to the slides. You can use that kind of a process. Because of relational closure, you can make things much more complicated and convince yourself that you've applied all the rules of logic correctly. And it gives you kind of a systematic approach to finding what's wrong, modifying your assumptions, going back, and testing your new assumptions or your slightly revised assumptions. And that can help move to a new system like that. Relational closure is very important to everyone's accustomed to working with relations as sets, and the closure's important. If you, just like in algebra, if you have, you multiply one number times another number, you always get a number. Similarly, in algebra, if you divide by 0, you get something that's not a number, and that represents a lot of complexity in mathematics because you don't have a number to work with. You have to avoid that case. One of the nice things about relational closure also is that you're not restricted to combining only relations that the schema designer considered to be related. For instance, in a more object-oriented model, you'd expect to have references from some data to some related data, and you would need to understand that relationship and what it meant. And that's very context sensitive, again, and context sensitive is very hard to work with between systems of revisions and so forth. Whereas with relational data, you can combine the data in new and different ways than any designer thought ahead of time would be useful to do. You can make arbitrarily complex expressions, including functional relationships, everything else, and that's a lot more powerful than being restricted to the preconceived ideas of what data is related and therefore needs to be linked with references in an object-oriented model. That's a much less constrained view, especially reporting. Again, I'm back to the context sensitivity, and relational operations where you can combine using logic are much more valuable because typically the meaning of data, if you're using flat files or XML storage or whatever else, it's likely that the actual meaning of the data depends on a lot of things that in the real world are going to change. The user who entered the data, what fields the user saw when they were entering the data, the labels of those fields, how they interpreted those fields in the context of the user interface, the specific version of the specific application that interpreted what the user input after that point, and the application's internal data structures. All these things change realistically more often than the data schema and that kind of thing. The application's internal data structures are just less permanent, constantly open to revision. Usually they go through a testing procedure, but that testing procedure is not going to catch potential problems or subtle changes in the meaning of data that might happen over a long period of time. And could be done by potentially more people than would be modifying the schema of a centralized database. So that's why context sensitivity is so important. And that's what using logic allows you to step back and use facts that are true in the real world out of the context in which they were originally entered. And that is, if we look back at the example here, you can see that the assumptions we made are not very context specific. We're making the assumptions these can come back out to real world facts, and that's why we're able to deal with them. And they're going to have meaning regardless of how the application might change or some other implementation detail might change over time. So the context insensitivity is a big win. If we look back at the goals, then a lot of these things we were able to achieve much more successfully with logic and relational theory than with some kind of object-oriented model, for instance, of storing the data, object relational mapping kinds of things that impose the application's internal data structures on the schema design. So I think we've achieved a lot of those goals here. It's much more intuitive. You work with predicates, not with meaning individual attributes. It's practical. Data migrations and reports are done all the time by DBAs, developers, those types of people. It's totally unambiguous. It's much more flexible. You aren't restricted to the preconceived design relationships. And it's fairly simple. And it helps achieve data independence because our reasoning didn't depend on the data in the tables. So this is the material so far. I'm kind of opening it up for questions or comments.
What do you deal with multi-set semantics?
Multi-set semantics. So that's a good question. The easy answer is that you use multi-set semantics, first of all, to explain it's a set that allows multiple instances of the same value. So it's also called a bag. And they're much more difficult to work with. So for instance, an easy way of mitigating those factors are using distinct, which simply makes it a real set. In Postgres, that's implemented with a sort. It's not always very practical for huge data sets because it is, in theory, fairly optimizable in many cases, and sometimes doesn't need to be done because it could be proven maybe that there would not be a multi-set in the result, that it would be a real set. but it's very hard. The optimizer is not going to actually be able to do that in many of the cases. Perhaps due to some peculiarity of the SQL standard or something else. So it's not perfect. And the other thing is that even if you use distinct everywhere, there's still sort of transient values in between your operations that could be operating on multi-sets if you're not careful, or could somehow create some transient value that's actually a multi-set. So, but yeah, that's a good question.
All right. So given your goals of the data model here and what you talked about, do you think it was a mistake for the SQL committee to settle on 3-value logic as opposed to, say, 5?
Well, that's a big question that a lot of people debate about. It's nulls themselves have significant practical value in the sense that in Postgres they're implemented in an efficient way if you have a sparse stable. That's really could be viewed as more of an implementation detail. Nulls make it much harder to optimize. They also make it much harder to reason about what something actually means. I would argue that nulls make the implicit assumption that on the meaning of attribute concept. For instance, the idea that everything is just an AND predicate, you can remove arbitrarily some piece of some proposition, one of those AND components, and it will still be true. And that works for some data, not for others. It makes it difficult to reason on the data as a set, and usually requires exceptions. There's lots of very unintuitive behavior. If you're using in and not in on a subselect, that's one of the least intuitive things I can imagine. It's the type of thing you constantly need to reference back, do quick tests to see what you actually think the null is going to do. It's got lots of kind of magic behavior. But at the same time, unless we had a system where it was much easier to have many tables and to optimize everything correctly as the number of tables you need to represent your data without nulls, it does pose certainly some practical problems.
But, I mean, don't you think it would have been, because of the meaning of the attribute here, and I slightly want to take exception with one of the formulations you have, because it's not strictly true that you can remove these things and the truth value remains the same, but the truth conditions remain the same.
I'm not sure the exact distinction you're making.
So
the truth value being the result of the predicate,
right,
when it's evaluated.
Right. What I mean, because in some cases when you remove that and, you of course change the meaning of the.
Correct. I think you've lost a little bit of meaning.
Right.
But I believe that in the simple case of an ANDed list of predicates, if you remove one of those, it will be still true. It will have a slightly less valuable meaning, because rather than saying there exists some location L at such that company C is located at L, where L is a bound variable and C is a free variable. If you have a formulation like that, then you're still, it's still true to say that there exists a company C, right? You don't say as much, but I think it's still true. And it's also
it can be, but I mean, you picked your example in that case, because if you turn it around the other way, it isn't still true.
Correct. I mean, that's part of my point, is that it's a weak way of, I'm not advocating that you analyze the meaning of attributes. I'm actually doing the opposite here. So I think we're in agreement about that. It's a dangerous thing to make those assumptions, but we implicitly do all the time. Or I shouldn't say everyone, but it's very common, you see a spreadsheet, you implicitly assume that, you just highlight one section of that spreadsheet and you can copy that somewhere else and it'll still be true. Well, that's kind of a dangerous thing to do, and that's my point, really, with this slide, is that that's, a very dangerous path to go down, and that it's flat out wrong in a lot of cases. So I think to answer your first question, whether I think it's a mistake or not, I certainly don't think it's ideal, and I think that you should avoid nulls where you can, and you should recognize the assumptions you're making when you use them. And I think it's very difficult to reason based on that. I'd be interested to kind of see how optimizable you could get if you kind of avoided the counterintuitive nulls. But I think that's still kind of open line of research.
Earlier you said join is equivalent to and. Isn't that only really fully hold true with inner joins? I mean, as soon as you allow any kind of outer join, does it become a kind of disjunction?
Well, that gets back to the nulls question. An outer join uses nulls, and it's again one of those. You're implicitly assuming that those.
Well, not necessarily. It's back off to the fact that it does come from set theory. A lot of this is the SQL equivalent to where you have like the set functions, where it's this function while this holds, or this value, or this other function while this holds, and that's what a lot of times that equivalent is. I mean, it does deal with nulls, but it's kind of a this if this. The result has nulls, but the main reason behind being able to do that is that you want to take the data, work on the data in different cases.
The difficulty with an outer join, though, is that one entire side, if you say that it's the predicate of R1 and the predicate of R2 and it together, would be the meaning of that. Well, the predicate of, or the data that you're getting from the operation of the join is going to be of an outer join. For some of those tuples, is going to be all null. So, something and null. Well, SQL standard defines null, one and null to be null, true and null to be null. So I agree with you that leaves you in an unknown state. I think that that's a consequence of nulls, and I think that there's other ways of accomplishing the type of thing that you'd be trying to accomplish with an outer join. Specifically, you can use, not that this is supported by SQL or Postgres, but if you were able to have relation valued attributes, then you would join and group the values at the same time, and you'd be able to operate on empty relation or relations with some values